It is Monday, March 24th. This is CS 746, Perspectives in Data Science, and today's lecture is on principal component analysis. We'll go ahead and get started. This is how much questions there are. This could be a short lecture, or it could fill up the time. Good morning. So what is principal component analysis? It is another way to reduce the number of features you're looking at. So this lecture starts off with a discussion of the curse of dimensionality, which I think in the fall semester, this comes out close to Halloween. So it's an appropriate topic to cover at Halloween time. But in the springtime, it's just, well, it's after spring break. So curse of dimensionality doesn't make a whole lot of sense in this semester, right? Anyhow, the curse of dimensionality. Increasing the number of features does not always improve your accuracy of your regression or your classification, whatever you're trying to do with your data, right? In practice, the inclusion of more features might actually lead to worse performance. The number of training examples required increases exponentially with the dimensionality, right? So the number of, let's see, for the number of bins per feature increases as k to the power of d. So if we have 3 bins, we're trying to classify in this case, right? So we're going to assign labels to things, right? And if we have 9 samples, that fits nicely with, probably 3 samples in each bin, right? If we go to 3 squared bins, we have 9 bins, and now our 9 samples are looking a little more sparse. Not too bad. When we go to 27, when we go to 3 cubed, right, we end up with, our 9 bins, our 9 samples are spread out amongst 27 bins. If we go to 4 dimensions, of course, we're at 81. Bins that we could throw those 9 samples in. And so now we have a whole bunch of empty space, and we're not able to do a good classification. Sparseness. Sparse data is low density, scattered. A high percentage of variable cells don't contain any useful or actual data, right? You're fundamentally full of empty or not available values. You're basically outer space, right? Mostly empty. N-dimensional space, as n grows, the data becomes more sparse. The distance between the data points grows, right? So the implications are that optimization problems become infeasible as a number of features, because each feature has to be thought of as a dimension in your model, right? So every feature that you're looking at is another thing that can vary, another maybe orthogonal dimension that things can change, right? Another column in your matrix, if you're doing matrix theory, right? So matrix algebra, sorry. So as the number of features increases, it becomes more and more infeasible. To the absolute scale of inherent points in an n-dimensional space, as n grows, the possibility of recognizing a particular point or even a nearby point falls, right? And eventually becomes, very, very difficult to find anything. So the objective, of course, is to figure out how many features, dimensionality, number of features, what is the best performance? How many features should we have to get the best performance of our model? If we don't put enough features in, we can't predict much of anything. If we put, obviously if we put 0 features in, we can't do any predictions, right? If we get 200 features in there, then our data is going to be so sparse that we won't be able to do anything with it, right? So different methods. We've seen different methods to reduce dimensionality, right? The 2 main ones are feature extraction and feature selection, right? So dimensionality reduction, the idea is to eliminate some of the features of the data set. Ideally, this set still contains everything we need to predict our target variables. Fewer features means we have more efficient, more accurate estimates. It reduces our output variability. It reduces the learning complexity of our models. So one way we can do this is to use, we're going to call the covariance matrix, where we look at how each feature varies along with the other, right? This is another way to deal with correlation between features. We've talked about the variance inflation factor before, right? So how do we measure multicollinearity? And the answer is we measure that using the variance inflation factor. And we have variables or features that are supposed to be independent of each other. And if we are not independent, if they vary together, they move collinearly, highly correlated. This makes their coefficients more unstable. Of course, our metric is the variance inflation factor. We take r squared, we subtract that from 1, and we invert it. And this gives us a number for each feature, j, whatever that feature is. Variance inflation factor for that feature tells us how much it would be explained if it was the response variable. So if we tried to run a linear regression on this particular feature, right, how well would we be able to predict that variable using the other variables in our model? Right, so it's basically what the VIF is trying to show us. So it's based on the coefficient of determination with the other features here, right? Our first step in dimensionality reduction is, of course, the covariance matrix. It gives us an idea of the number of strongly related features. So, we can look at, we've already done a correlation matrix. We're going to do a covariance, which is similar, but gives us a stronger metric and shows us which features are best explained by all the other features, right? So correlation matrix shows for pairs of features how strongly correlated they were with each other. We want some sort of a metric that shows us how much each variable is explained by all the rest as a group, right? So this gives us details of all the independent features. It gives us an idea of the number of strongly related features, so that those features can be thrown away or deprioritized, as you might prefer. It provides an idea of the correlation between all the different pairs, and it is a necessary step in calculating eigenvectors and eigenvalues. Good German words getting in here. Well, half German words getting into the class. Right? Covariance is not correlation. They are related. You can see down here the correlation of x and y is the covariance of x and y divided by the standard deviation of x times the standard deviation of y. All right, so there's a formula that gives us correlation. Correlation is basically covariance normalized to the range of -1 to +1, right? The covariance of x and y is for variable x, how much does it vary from the mean value of that variable x, and for variable y, how much does it vary from its mean, divided by the sample size n for a population, or divided by n-1 for a sample, right? We can get fairly large, right? Now, in dimensionality reduction, we got two ways to do it. We talked about feature extraction, where we're finding a set of new features, which is what we're going to do in PCA, where we find a new set through some mapping from the existing features. We've also done feature selection in the past. We've seen this with, variable selection. We did 2 whole lectures on that, where we basically have our variables x1 through xn, and we do some transformation where we basically throw away some of the features and pick a subset of the features, right? But we're not going to do that with PCA. We're going to pick a separate set of features that incorporates the most useful information from our original features and throws away the least useful information, right? And again, in both of these cases, the number of features, y through k, xi through xk, is significantly less than the original number of features. The whole point of feature selection, of dimensionality reduction, is to decrease the number of features that we have to deal with. So in doing feature extraction, linear combinations are particularly attractive because they're easy to compute. They're easy to analyze, analytically tractable, just because we make that sounds like fancier than easier to analyze, right? So given x, remember the real numbers, we find a k by n matrix T such that y is the T times x is a member of the real numbers where to size k, where k is significantly less than n. Again, this diagram simply restates that. We've done some transformation on the x values where we get new features that are significantly smaller size. This is a projection from n-dimensional space down to a k-dimensional space. So imagine a three-dimensional object, you're casting the shadow, right, on the table. And we're trying to look for the most useful projections to that lower dimensional space, right? From a mathematical point of view, we're finding an optimum mapping on y equals f of x is equivalent to optimizing an objective criterion. Different methods use different criteria. For instance, we could say we want to minimize the amount of information that we lose. We want to model the data as accurately as possible in a lower dimensional space, right? Or we could be looking for maximizing discriminatory information. We want to enhance our ability to discriminate between classes of our data, right? So we want to do what's edge finding is another term we're doing that, right? We're looking for where the boundaries exist versus maintaining as much information as we can. There are some popular linear feature extraction methods. Principal component analysis. The goal of PCA is to preserve as much information as possible. There's linear discriminant analysis, seeks a projection that best discriminates the data, best, draws the boundaries. And there are many other methods, which we will not be discussing in this class, but which are out there for you to look at and use in your career as you go forward as a data scientist. You can make features as independent as possible. ICA, which sounds like an insurance company to me, but yeah. Retaining interesting directions or projection pursuit. Embedding to lower dimensional manifolds. The ISO map, local linear embedding, or LLE, are ways to do this. So the rest of our lecture, we're going to focus on PCA, right? And so PCA, in a nutshell, is an exploratory data approach to reduce the data set's dimensionality to probably 2D, 3D, maybe 4D, if it's appropriate, right? For making predictive models, it is a linear transformation of the data set that defines a new coordinate rule such that highest variance by any projection of the data set appears to lay on the first axis, the second biggest variance on the second axis, and so on. If you recall, we did a three-dimensional plot of three different features in the iris data set early on in the class, right? And we could see sepal width, sepal length, and I think petal width plotted, and we could see there was kind of this cloud of data, and the iris setosa was down here, and the versicolor was here, and the virginica was up here, and there was kind of a cloud that kind of went up and to the right in our data set, right? And so the idea of PCA is to take that cloud and say, where's the longest dimension of the cloud, and where's the second longest dimension, and the third longest dimension, and so on, right? And we're trying to reduce that by reorienting the axes of our data such that the longest variance is on some combination of sepal length, sepal width, and petal width, right? So we're calculating some sort of a feature. And again, as I said before, when we start talking about different kinds of features, we're talking about hidden models, right? We're talking about petal size is being represented by petal width and petal length. But petal size could also be, or petal shape can, if it's wide at the bottom and then long at the top and skinny, right? You get different kinds of descriptions of the size of a petal of a flower, right? It's kind of difficult to describe with just, a couple dimensions, but PCA is trying to find that underlying kind of meaning about it, right? It's also known as a hidden Markov model. If we get into any of your class, anybody discuss Markov chains, Markov models? A couple of you done that in your undergraduate classes, yeah? Okay, and so the idea of a hidden Markov model is that there is some process going on that we don't understand what it is. We need to find out how that process works, right? So we're uncovering something that's behind the scenes, right? Classic example, understanding the genetics between, how DNA codes, features in a person, right? We can look at a person and say they're tall or they're short or they're wide or they're thin or whatever, right? And there's genetics behind that. There's other things that are going on. We're finding the model that's underlying the shape of that being, right? So PCA is the most common form of factor analysis. Sorry for the little sidetrack there. The new variables and dimensions are linear combinations of the old ones. I'm not trying to do curves or anything fancy like that. They are uncorrelated with one another. That it means that they are orthogonal in the original dimensional space. And orthogonal, of course, means right angles, right? They are capturing as much of the original variance in the data as possible. And as if it wasn't obvious, they're called principal component analysis, the principal components, right? Principal components because they are the components that are the main features, right? And so on. Yes. I'm sorry. So the first principal component is the direction of greatest variability or covariance in the data. The second is the next orthogonal uncorrelated direction of greatest variability. So we first remove all the variability along the first component. Then we find the next direction of greatest variability. And then we remove that second component. And then we find the third greatest variability, and so on and so forth. So the principle, we're doing a linear projection method. To reduce the number of parameters, we're transferring a set of correlated variables into a new set of uncorrelated variables. We're mapping our data into a space of lower dimensionality. And this turns out to be actually unsupervised learning. We can tell our model, go figure it out. And we don't have to do anything. It just does the math, right? It's actually fairly simple, straightforward. Right? It can be viewed as a rotation of the existing axes to new positions in a space defined by the original ones. The new axes are orthogonal, represent the directions with maximum variability. Here's an example, original variable A, original variable B. This is a two-dimensional example. So we're not seeing any reduction in dimensions here, but we are seeing that, our original variability, the data is much more spread out along that axis. And then we find something that's roughly right angles to that, and that is our principal component 2, right? So we're using PCA in various different places. First, to reduce the number of dimensions, to remove the cursive dimensionality, get us a better model, right? This helps us find patterns in our high dimensional data set, right? It helps us visualize our high dimensional data. It helps us ignore noise, because in that high dimension, some of our data is just meaningless noise. Well, if we find out that there's just stuff that's random variations about the mean, we can throw that away with PCA because it'll cancel itself out and become a less important feature. It'll improve our classification. It will give us a more compact description of our data. It might not be intuitive, but it will be compact, right? And again, it captures as much of the original variance in the data as possible. So our steps are, first, we start by standardizing the data. It doesn't do any good to do PCA if some of your features are on a scale of centimeters and the other scale is on kilograms, because one is so much larger than the other in realistic things, right? So we have to normalize everything or standardize it to a standard range for everything. Then we can build the covariance matrix of all of our features. We find all the eigenvalues and the eigenvectors for the covariance matrix. And then we plot our new vectors on that scaled data. As an example, we have 100 students in class. We can measure all sorts of features. We can measure, what their grade is, what their age is, their height, their weight, their hair color, number of teeth they have in their head, right? How many noses they have, how many ears, so on and so forth, right? A lot of those quasi-constant features, right? Many of the features are not relevant to describe the student. So we want to find the critical features that characterize a student. So some analysis, based on different features. Every student has a vector of data that defines him or her. So again, I have a specific height, I have a weight, I have a hair color, which is a lot grayer than it used to be. I have a particular grade that I achieved in school, right? And so we can list this as 181, 68, black 99, so on and so forth, right? So each column then in our data is one student. So we have 100 columns because we've got 100 students, right? We have an m by n matrix. Each student lies in an m-dimensional vector space. Features to ignore. Linear features or linearly dependent features. Leg size and height. are largely collinear with each other. Taller people have longer legs, right? Noisy features that are constant. We like, measure how thick our hair is, right? How much hair we all have left, right, on our head, right? That's largely constant for most of the people, right? The number of teeth are, well, it's not completely constant, but it's very much quasi-constant, very close to constant, right? In other words, your teeth, the number of teeth you have in your head doesn't change after a certain point, unless you start knocking things out by taking up boxing or something like that, right? So features that we do want to keep, things that are non-collinear, that have low covariance, features that change a lot, that have high variance, in other words, the grades, right? So the eigenvectors and the eigenvalues of the covariance matrix describe the source of our principal component analysis. An eigenvector is the direction of the new attribute space, and the eigenvalue is how big the attribute is, right? So vector is direction, value is size, magnitude. So the PCA's main objective is to reduce the data's dimensionality by projecting it into a smaller subspace where the eigenvectors form the axes. However, eigenvectors only describe the new axis directions. An eigenvector always has a size of 1, so we need to show the eigenvalue that tells us which vectors are more important than others, right? And the eigenvectors with the highest values, the ones that we want to keep. The eigenvectors with low eigenvalues are the ones we say are less useful, not helpful in our model. We're going to throw those away after we build our PCA, right? We use PCA for visualizing data, for compressing data. We use it for reducing the noise in our data. It's great doing data classification. It's been used heavily in image compression, right? We can do a lossy compression algorithm using principal component analysis. We find the important features in the image, and we keep those features and throw away things that are less important, right? Face recognition is also a great PCA task. Any kind of image recognition or something like that, right? Where we're looking for something in that image. PCA is useful in that case. So the rest of our class, it is 11:25. We're moving fine. Great. Might have you out of here a little early today. I'm sure you're all happy to know that, right? So step 1, we get the data. Step 2, we compute the mean vector of the data. Step 3, we subtract the mean from all the given data. Step 4, using this subtracted data from the mean, we calculate the covariance matrix. Step 5 is now we find the eigenvalues and eigenvectors of that covariance matrix. And step 6 is we choose the components and form our feature vector. And then step 7 is we finally derive the new data set, the new components that we've chosen to use, our principal components. So we're going to do a simple problem. We have 2 variables we've measured. Call them X and Y for now, right? So the first dimension is 2, 3, 4, 5, 6, and 7. The second dimension is 1, 5, 3, 6, 7, 8. You can see that these are kind of correlated with each other, but they're not 100% correlated, right? So we're going to compute the principal component using the PCA algorithm. So our given feature vectors are x1 is 2, 1, x2 is 3, 5, 4, 3, 5, 6. We pair up all our data, right? And these are our data points. Now we calculate our mean vector. How do you calculate a mean vector? Well, you sum each row in your vector, and then you divide by the number of samples we have. So 2, 3, 4, 5, 6, 7, add those together, divide by our 6 samples. 1, 3, 5, 6, 7, 8, add those together, divide by our number of samples, and we end up with 4.5 over 5. So that is our mean vector. So that's the average of all of our data points that we have, right? So now we're going to subtract that mean vector from all of our given feature vectors. So our first feature was 2, 1. So we're going to subtract 4.5 from the top and 5 from the bottom. So we get minus 2.5 and minus 4. For x6, that value was 7 over 8. So we're going to subtract 4.5 from 7. We're going to subtract 5 from 8. We're going to get 2.5 over 3. Those all, you do the math, you'll see that this is theoretically correct. If there's an error in here, I'll be very surprised. I've been using these same slides for several semesters now, and I think they were stolen from a professor who used them probably for 400 or 500 years before that. So anyhow, so these are our feature vectors after subtracting the mean vector from this. So now everything's kind of like normalized as the distance from the mean vector as to what our data point is, right? Now we're going to calculate our covariance matrix. Our covariance matrix is given by the sum of x sub I minus the mean over x sub I minus the mean transposed over n. So what does that mean? Well, we're going to take x sub I minus 2.5 and minus 0.4. We're going to multiply that by itself transformed. So 2.5, 2.5, 6.25, 4 times 2.5 is 10 and 10. Then, of course, 4 times 4 is 16. Right? So we calculate our individual values here. Yes, okay. Now our covariance matrix is then add all of these together, these new matrices here. We sum all those together and divide by 6 to get an average. So 6, or I'll start with this top right corner here, was a 10, 1, 0.5, 3, 7.5. We add all those together, we get 22. We divide 22 by 6, we get 3.67. So this is our covariance matrix. Again, sum up the difference of summation of every matrix multiplied by its transposition, and then we divide that by the number of samples we have. So now we want to calculate the eigenvalues and eigenvectors of the covariance matrix. And the way to do this is an eigenvalue for the matrix M is an eigenvalue if it is a solution of the characteristic equation M minus lambda, where lambda is the term here, identity. Anyhow, I don't think that's right. But we subtract, again, our matrix where everything in here is zeros except that main diagonal. And there's some value on here that we can subtract from everything that will give us the best sum, right? So the solution of our equation is this minus this equals 0. Therefore, 2.92 minus lambda, 3.67 minus 0, 5.67 minus lambda equals 0. This is the characteristic of the matrix, not the matrix itself. We have just vertical lines here, right? So in order to calculate the characteristic, of course, we add the diagonals, subtract the anti-diagonals. 2.92 minus lambda, 5.67 minus lambda minus 3.67 times 3.67. In other words, we've added these two, subtracted these two, right? That gives us 0. We get a quadratic equation where lambda squared is minus 8.59 lambda plus 3.09, and that solves to 0. So we can use the quadratic formula to solve that. We get two possible values for lambda, 8.22 and 0.38. And the eigenvalues for our vectors are therefore lambda 1 is 8.22 and lambda 2 is 0.38. So the eigenvector with the biggest eigenvalue is the one we choose as our principal component, right? So we solve these two equations. We get 2.92x is 8.22 minus 3.67x2 is equal to 8.22x1. 3.67x1 plus 5.67x2 is equal to 8.22 of x2, right? So we're using the covariance matrix is the eigenvalue times the eigenvector is the original, is the equation we're looking for, right? So when we simplify these, we get 5.3 of x1 is 3.67 times x2, blah, blah. We have a couple of equations. We can then do solve those equations together, and we find that x1 is 0.69. And so therefore, the eigenvector is x1, x2 equals 2.55 over 3.67. The principal component for our given data set is therefore this feature. So the base So have we reduced our features yet? No, we still have 2 features, right? Right. The reduction doesn't come in yet. PCA simply reorients all the data into a new framework, but we can then have that oriented in a way such that our biggest variance, principal component is the first axis, second variance is on the second axis, and so on, right? So the areas of variance in the data, right, where the most variances in the data is where items can be best discriminated. And the key underlying phenomena observed, this is the area of the greatest signal in our data. If 2 items or dimensions are highly correlated, they're likely to represent highly related phenomena. If they tell us about the same underlying variance in the data, then we can combine them to form a single measure. That's a reasonable thing to do. Use the principle of parsimony, or the simplest model is usually the best one, and reducing the error, right? We'll have lessen our risk of making mistakes by having too much useless data in there. So in a combine related variables, focus on the uncorrelated or independent ones, especially those along which our observations have high variance. We want a smaller set of variables that explain most of the variance in the original data in a more compact and insightful form, right? So again, what if our dependencies and correlations are not very strong? What if they're not very direct? What if we have a lot of variables, only a few variables? What if we have 10,000 variables, right? We're looking for the phenomena underlying the observed covariance. Once again, the thing that are uncorrelated or independent, those are going to show high variance, right? These phenomena are called factors, or principal components, or independent components, depending on the methods used, right? We've done PCA. They're the principal components. We can also see independent or factors, right? And again, we've done PCA, simple, quick and dirty example here in the class. Now, if we were doing an ICA, we would look at things that best differentiate, right? Which would be a completely different one. So our first principal component retains the greatest amount of variation. Our kth principal component retains the kth greatest fraction. The kth largest eigenvalue is the variance in the sample along that kth principal component. Another way to look at this is consider the least squares, right? We've got a cloud of data. We've done a series of least squares. We find a least square, of the first greatest variance. We've eliminated that. We take that out. We calculate another OLS regression for the second most variance, and so on and so forth, right? And every one of these is now orthogonal to the other in some higher dimension space. If we look at it this way, we get principal component 1, 2, 3. If we have 10 features we're looking at, we do a PCA, we'll end up with 10 principal components, right? And we always arrange these so that the first principal component has the most variance, and the last principal component has the least variance. If we throw away some of these values out here, right, we lose some information. But because there's not a lot of variance out there, we don't lose much variation, right? So if we have n dimensions in the original data, we calculate n eigenvectors and n eigenvalues. And now we choose the first p, where p is significantly less than n, and that gives us a new model. So how many variables would you choose given this data set? How many people say keep all 10 of those principal component analyses, principal components? I see nobody voting for all 10. How many say just take the first one? I see nobody. How many say, maybe 3 or 4 is about right? I see a few hands go up. Yeah, I would say we go down about 3 or 4. When we get down to here, this doesn't provide a lot more than this one. 7, 8, 9, and 10. Basically, there's not much more information. Any of those in the one following after it. So this is, in a sense, we can call this a scree plot, where scree is, if you go mountain climbing in the Rocky Mountains sometime, you'll find at the bottom of a cliff, there's this pile of loose rock and rubble, right? That's called scree. And so the nice solid cliff is up here. That's where your good data is. When you get to the bottom of the cliff and everything levels out because the scree is just loose rock, it can't build up strictly, that's not the most useful information. You can safely throw that away from your model. On a larger scale, this is the Colorado Rockies, and this is all eastern Colorado and Kansas here. Right, so basically this whole state is scree off the Rocky Mountains, right? So we can ignore Kansas. I don't think that was came out quite right. Anyhow, but point being that we're looking for the components where there is significant information given by that particular feature, right? So in this case, we'd say we're going to pick probably the top 4. We could go even stronger and say to pick the top 3 because our variance here, this is explaining less than 10% of our variance in principal component 4, right? So you could go even further if you wanted to. Principles component analysis, choose the eigenvectors, the covariance matrix that correspond to the largest eigenvalues. The eigenvalues correspond to the variance of the data along the eigenvector directions. Therefore, PCA projects the data along the directions where the data varies most. It preserves as much information as the data as it can by preserving that variance. Because it maintains that variance, right, is maintaining the information in that. Again, U1 in this case, X1, X2 are 2 independent features, or theoretically independent, but actually they've got covariance between them, right? So the direction of our maximum variance is U1, U2 is orthogonal to U1. The principal components are dependent on the units that we use to measure the original variables, as well as on the range of the values they assume. Therefore, your data always needs to be normalized prior to doing principal component analysis. Make sure everything is on the same scale, right? Common normalization is take all your data. If you've got a height, you transform it so that the mean height is set to 0 and the standard deviation is set to 1, right? And so you've just reoriented all your variables to a standard normal curve by simply subtracting each feature, the mean from each feature, and then dividing by the unit standard deviation, right? So this will take any normal distribution curve and convert it into a standard normal with a mean of 0, standard deviation of 1, right? And that is, in fact, the end of our lecture on principal component analysis. I'll stop and ask if anybody has any questions. Yes. Yes. You want to use covariance to calculate your eigenvalues and eigenvectors because the correlation has already been renormalized again. So you're not getting as much information out of that. That's my simple, quick, and dirty answer as someone who's just lecturing on this and didn't write a lecture. Well, you could use that, I don't know. There are different, of course, we talked about there's linear discriminant analysis where you're trying to use different things, right? So you'd use different features or different information in the data to do your discrimination on a linear discriminant analysis as opposed to principal component analysis, right? So your answer is really, you know, in what situations is it appropriate to use correlation? I don't know. Yeah. You let me know if you find out. What's that? I imagine it gets used sometimes. Yes, yes. Although, again, since correlation is nothing but recalculated covariance, right? It's easier to use covariance just directly, right? Yeah. Any other questions? Okay. So yeah, PCA preserves much information. The data is preserved by and that was the end. Yes. Okay. Grading proceeds apace on the midterm. I was a little slow getting the rubrics out, so they've been working on that over spring break, which I feel bad about. But they're working on that. The grades in this class were relatively good, especially when I compare to the other class I teach, which is advanced topics and data storage. We had a little bit harder time getting through the midterm in that one. But we're going along pretty well, so I think we're going to be seeing some good grades. I know there's a couple of you that were sick for the exam, and need to schedule a makeup time someplace. So we'll discuss that here after we clean up our lectures. So right now, I'm just going to go ahead and drag up. We have an attendance quiz for today. I haven't looked closely at it. But if you go out there and click on that, you should be able to find the quiz, and it will tell you whether I successfully discussed every topic or not. We'll find out. I'll pull up the quiz here myself and look at it. Okay, those are good questions. All right, so once you finish that, you can go ahead and take off. Let's see, get a look online because there were a few people online. Ugh. I forgot to turn off sharing. I've just accidentally given all the online people credit for attending today. What's that? Oh, the project checkpoint. Oh, great. Okay. I will discuss that. It obviously. Yeah, you're good to go. So project milestone 2, but the checkpoint. We'll discuss that. I'll get back to you. Yeah, okay.